Every physical object occupies space on the inside, its volume, but the outer boundary where that object meets the world is its surface area. We interact with this outer skin constantly. It determines how many gallons of paint cover a wall or how much aerodynamic drag pulls against a car on the highway. Calculating the exact size of this boundary is difficult. A standard tape measure cannot easily lay flat across an object full of sharp angles, internal corners, or continuous curves. Mathematicians solve this complexity by using a tool called the net. They imagine unfolding a three-dimensional object until it sits entirely flat in two-dimensional space. This reveals the universal rule for surface area. Break a solid down into its flat net, calculate the area of each individual piece, and add them together. The cube is the simplest starting point. Because of its perfect symmetry, every edge is identical, and every face is an equilateral square. A cube's net consists of 6 identical squares. To find the total area, you calculate the area of one square, side squared, and multiply that result by 6. A rectangular prism, like a shoebox, has varying dimensions, but it follows the same predictable logic. Its net reveals 3 distinct pairs of identical rectangles. You have the top and bottom, the front and back, and the 2 sides. The formula simply adds these 3 pairs together. This unfolding logic applies to any flat-sided shape, including triangular prisms. You add the area of the 2 triangular bases to the 3 rectangular sides. For any object with flat faces, finding the total surface area is a straightforward addition problem of basic geometric shapes. But the question is how to apply a flat net rule to a shape with a continuous curve, like a cylinder. We find a hidden flat surface by peeling the curved side off and flattening it into a rectangle. Its height is the cylinder's height, and its width is the base's circumference. Combining this rectangle with the 2 circular bases gives the total area. Cones are more complex because they taper to a single point. To measure this surface, we need a specific metric, the slant height. We find this by visualizing a right triangle inside the cone. Using the radius and the vertical height, we apply the Pythagorean theorem to calculate the hypotenuse, which gives us the slant height needed for the formula. Even curved shapes can be translated into flat nets once we use pi and triangles to account for their dimensions. Then there is the sphere. It is perfectly round, possessing 0 edges and 0 vertices. The sphere is the one shape that breaks the unfolding rule. It is physically impossible to flatten a perfect sphere's surface into a 2-dimensional net without stretching or tearing the material. Archimedes solved this problem by looking for a different kind of geometric relationship. He discovered that the surface area of a sphere is exactly 4 times the area of its own cross-sectional circle. Because a sphere cannot be unrolled, its measurement requires us to move beyond simple nets and instead use the proportions of its internal radius. Engineers and the natural world default to these specific geometric shapes to solve problems of efficiency. For any given volume, the sphere has the smallest possible surface area. Nature uses this to minimize exposure to the environment. It is why soap bubbles are round and why igloos are shaped to trap heat. In contrast, biological structures like the human lung use highly folded surfaces to do the opposite. Lungs maximize surface area within a small volume to ensure the body can absorb as much oxygen as possible. Since we are measuring a 2-dimensional skin on a 3-dimensional object, the final result must always be expressed in square units, like square centimeters or square inches. Understanding surface area allows us to calculate exactly how much material is required for a project, how heat moves through a structure, or how efficiently a system exchanges gases. It is a practical tool for navigating the physical world.